Hello, my name is Luis, and here at the University of Porto I'm looking at ways of making reconfigurable systems easier to use. Circuit design is notorious for being highly specialized, labor-intensive work. High-level synthesis has allowed developers to transform their C code into RTL descriptions, enabling easier and faster ways of developing computing kernels. This has lowered the bar of entry for the creation of increasingly heterogeneous and more complex computing systems. FPGAs, through the available dynamic partial reconfiguration feature, permit that these kernels may be instantiated on demand by the application at runtime and removed from an FPGA's programmable fabric once they are no longer required, thus leaving space available for other kernels. By allowing for this time multiplexing of kernels, smaller and lower cost FPGAs can be used. This, however, introduces a problem: managing the availability of the kernels. Management has traditionally been a task left up to the application developers. One key problem is determining if the overhead of instantiating a kernel using DPR is worth the performance gains of using the accelerator, or if executing directly on the CPU ends up being faster. As embedded applications scale, tackling this problem manually becomes unfeasible. Frameworks have emerged that relieve developers of this burden by automating a process of profiling the performance of task execution on both the CPU and accelerator. These then use the results of this profiling for making decisions at runtime about which alternative to use. However, besides requiring long periods of time dedicated to this profiling, they do not solve one other problem. Both the manual approach and these frameworks suffer from a lack of portability. If the same application is deployed on a different device with different characteristics, the performance models produced by these frameworks become invalid. Every software update prompts a reprofiling of the system. This is where the Hofding tree comes in. It is an online learning algorithm for decision trees. This means that, unlike more traditional batch learning algorithms, it can constantly train on new data without requiring that the entire data set of previous data points be kept in memory. By using the Hofding bound, these trees can take advantage of the fact that a small sample can often be enough to predict the optimal splitting attribute. Additionally, it guarantees that, given enough samples, it will provide the same model as a decision tree batch learner. We propose to take advantage of the properties of this algorithm and perform not only the decisions of where to execute a particular function call at runtime, but also the profiling of the available options. This will allow for faster development, multiple platform support, and customized decisions, as every device will be trained independently. Different kernel usage patterns on a device will result in tailor-made models for that device. The process starts by using the decision tree to decide if either software or hardware execution should be used to target each individual function call. If the decision tree's confidence level in its decision is above a user-defined threshold, then the chosen component will execute the function and return the result. On the other hand, if the confidence level in the decision is low, the function is executed on both the central processing unit and the accelerator. Once execution is completed on one component, the other concurrent execution is halted. The result is then used to train the decision tree, increasing its confidence level in that region of the problem space. As inputs for the decision tree, we intend to use the values of the arguments of the functions, the size of the data they will operate on, as data transfer times should also be taken into account, an estimate of the arithmetic intensity obtained through static analysis, the order in which functions are called, whether or not the corresponding hardware accelerator is already loaded into the FPGA, and the temporal overhead of loading it via DPR. By encapsulating the original functions in wrappers, we can effortlessly introduce the execution of the proposed algorithm. Our work will focus on exploring and evaluating the validity of this approach through software implementations running in an auxiliary processor, and then via hardware implementations of the decision tree. We aim to increase the abstraction level given to programmers for the use of reconfigurable resources by shifting these management concerns towards the system. Thank you for your attention.